Hi, everyone, and thanks very much for sticking around for the afternoon session. So at the start of Astro 3D, I stood up and I made a bold claim that one of our goals is going to be nail F escape. We're going to figure out what the escape fraction of Lyman continuum flux is from high redshift galaxies so that we can figure out how many ionizing photons are available to reionize the universe. And as Lisa mentioned yesterday, one of our big overarching themes for Astro 3D is, of course, ionization. Now, I'm not going to claim that we've nailed F escape yet. And certainly, no group in the world has, and we're all working incrementally towards this big goal. But what we've done in the meantime, and because I've only got 10 minutes, if there's one thing that I want people to take away from this talk today is to understand why intergalactic medium transmission bias is a thing and why it's important. Okay, so and this work, of course, couldn't have been possible without Uroš Mestrik, who graduated from his PhD late last year, and Rob Bassett, who was a postdoc until very recently and is now working as a data scientist for CSL for all sorts of important things like making vaccines. And I'll be focusing today mostly on the results from Rob's paper from earlier this year, which is on IgM transmission bias. Now, the introduction to epoch of reionization isn't needed, thanks to Kath and Yusheng. So what I'm going to say here is that this red circle here shows us, when reionization is happening, but that ionizing photons that drove reionization, so these things that have a rest wavelength of less than 912 angstroms can never be observed from any telescope ever. Not JWST, not some futuristic thing on the dark side of the moon. We will never be able to see those photons. And that's because of the IgM opacity. So the IgM is not transparent to those ionizing photons from this era. So what we have been focusing on is observations and modeling of galaxies that are between a redshift of 3 and 5 to provide insight into that similar population of galaxies that exist at redshift 6 and above. So why does this matter? So the key equation in working out how many the number of photons that are available for cosmic reionization is over here in ion. It's a function of F escape, which is the escape fraction of Lyman continuum, which in turn is a function of the amount of transmission that there is in the intergalactic medium. Traditional studies will adopt a mean transmission. So they'll just take the average of all the different types of lines of sight, some optically thin, some optically thick, and everything else in between, take an average and say, okay, that's mean transmission, and take that into account when calculating F escape. What I'm going to argue today is it's really super important to take the bias into account, and that can get F escape wrong by a factor of 30%. Okay, so this is an image from Uroš's thesis where he's taken in the cosmos field. There's a parent sample of 407 galaxies here that all have a redshift above 3.42. And the reason that 3.42 is very specific is because that corresponds to a redshift where the U-band just samples Lyman continuum flux from these galaxies. So if you get any flux here in this U-band, then it means that it's Lyman continuum if it's all coming from that galaxy at redshift 3.42. So there was very careful work that needed to be done to weed out any interloper sources that may have been in the foreground in that U-band image. So in a nutshell, here's the schematic. So you've got some Lyman continuum emission coming from the center of a galaxy. You've got to take into account that ionizing radiation compared to the non-ionizing UV, stellar population, IMF, that sort of thing. Then you can go through some dust, which will attenuate it further. And then you hit the intergalactic medium that can cause some opacity. And if you happen to come across a damp Lyman alpha system or a Lyman limit system, that'll just completely block your field of view and no photon will get through to your telescope. If, however, you happen across a blue sky day and the photon goes all the way through, then you can detect Lyman continuum emission in your telescope, which is shown here in this U-band Claude's image. And so out of all of the galaxies that Ura started with, that parent sample, we ended up with only 5 that had clean Lyman continuum candidate emission. The fact that you detect Lyman continuum emission in a galaxy means that your line of sight to that galaxy must have been cleaner than average. It has to be. And so then if we take that as our representative sample of things that have ionizing escape and then apply that to the whole universe, you've got a bias automatically, because you're only taking the things that, you're only taking the galaxies where you can see something. So taking that to the next step, what Rob did was to look at these IGM transmission curves and created 10,000 of these. So you just roll a dice and say, okay, what sort of transmission do you get? And you sample for forest clouds along the line of sight. Some might be really thick, like damp Lyman alpha systems, which completely wipe you out, which are like down here. So for example, this green curve. Some are cleaner, blue sky. So then you get some transmission and then you measure the amount of Lyman continuum flux, which is in this band here. But if you were to take the ensemble of all of these curves, you get something like the mean transmission. But if you apply mean transmission to all curves, it's not representative at all about what happens, because some light does not get through all the time. And so adopting this would cause a bias. So we've defined this thing called transmission bias. It's the average TIGM for galaxies with Lyman alpha detected above a specific detection limit minus the traditional mean value that would be applied in most studies. So it's interesting, if you were to take all of those lines of sight and you plot them out as a histogram here, you can see that the black histogram shows that zero transmission is actually the most common scenario. And if you were to set a reasonable flux limit, say 27.9 magnitudes, which is pretty faint, but it's the maximum that you can extend to at the moment with modern telescopes for both Lyman break galaxies and Lyman alpha emitters. So Lyman alpha emitters have to be even brighter because on average, Lyman alpha emitters are faint. So by definition, if you've got as much Lyman continuum, it's going to you're going to need an even cleaner line of sight to be even to detect that thing. So if you detect, 1 minute. Okay, thanks. If you detect a Lyman alpha emitter in Lyman continuum, it means that it must have come from one of these very transparent lines of sight up here at the high end. So what does this mean? So what Rob did is take a sample of 1 million mock galaxies, looked at the difference between what you would get if you just adopted the average and what you would get if you were to correct it. And the difference is 0.3. So in conclusion, so this is Urosh's work. So we found that Lyman continuum galaxies tend to be either on or off. And this may be due to a variation in time. The galaxies may be going through a phase where sometimes they're on and sometimes they're off. It could be a morphology thing. So you happen to have a line of sight within the ISM of the galaxy that's clean. But there are very few galaxies that have been detected. If you just assume mean transmission, you get crazy high F escapes, almost up to 100%. But if you take in the maximal transmission, then you get something that's a little bit more reasonable, so between 4 and 30%. So our concluding statement is that the T bias rather than TIGM should be adopted for F escape calculations. And that's a really important input into the way that observations are modelled and how F-escape is then input into cosmological models as well. And I'll leave it there. Thanks very much.
Thanks, Emma. We have time for questions. Does anyone? Oh, okay, we got questions. So first question is from Elizabeth. Very interesting. How does your mean transmission function compare to other in the literature, for example, Maddow and Awe?
The mean transmission is modelled on an Awe. So it's the same mean transmission as has been calculated in the past. Most studies just use that mean transmission. Although some are starting to adopt like a minimal transmission, so looking at both mean and minimal, and that's what Erosh did in his paper, and we've taken it one step further by doing a whole ensemble of these transmission curves. Yeah.
We have another question from Luca. Very nice talk. Any chance to connect T-bias to the large-scale structure distribution of galaxies?
Yeah, really interesting. So T-bias essentially, so Luca, are you asking about, say, for example, can we look at transmission curves that are highly high transmission and low transmission curves, and then assume that things that have a low amount of transmission have more stuff in them? Is that what you're getting at?
Yes, he says
yes, he is. Okay, sorry, I can't see the chat. Yeah, so those sorts of studies have most definitely been done, and so this is something that people have looked at in the past by doing cross correlation of Lyman alpha forest data, and we do see that yeah, if you cross correlate Lyman alpha forest data, it does correspond to large scale structure. And in actual fact, I did that a very long time ago, right at the end of my PhD. So there's a paper from 2005, maybe, I'm showing my age now, where I actually cross-correlated high-pass galaxies and Lyman alpha absorbers, and found that there is a what would traditionally be called a bias, so an overproduction of Lyman alpha around high-pass galaxies. Yep. Around groups of high-pass galaxies. Yep.
All right, thanks, Emma. We should probably move on.